Okay, so if you just go back to this spring mass damper system and look at the final equation, by just looking at the equation, we can tell that this is a dynamic system, obviously. It's also a linear system because we have this y and y dot terms, but these are all constant coefficients, and there are no nonlinear terms in this equation. And also, this is a time invariant system, as long as these are constant numbers again. So we have a linear, dynamic, and time invariant system. Okay, so let me move on to our next example. This is the inverted pendulum. Okay, so we have this rigid bar, okay, and this bar can rotate around some hinge point here. So at point A, imagine there is a pinpoint here. So this can freely rotate around that point. So this is how we choose our coordinates. So we assume this vertical position to be, so this is the basis of our measurement for measuring the rotation. So our coordinate variable is theta. So this only has rotational freedom, right? So it cannot move other than that. So that means we need to consider the this equation to write the system equation, right? So we need to write the equation, the sum of all the moments acting on the system should be equal to the mass moment of inertia times the angular acceleration. And obviously the mass moment of inertia is the inertia of this bar with respect to its endpoint. Okay? So we start by writing the moment. So the gravity creates a moment, and this is how we can write it. So it has a certain weight, which is mass times the gravitational acceleration, mg. And the moment arm is this distance. So this is the moment arm. And that distance is equal to half of the length, which is L over 2, times the sine of this angle, sine of theta. So this is the torque due to the weight of the bar. And we can assume that there is a control torque here. So we have a mechanism somehow. This can be electrical or mechanical. There is an actuator there, and we can apply any torque we want. Okay, so and we call that TC. So we can make this a positive torque, a negative torque, or we can adjust its magnitude. So this is our control torque. So we just leave it as it is. So TC, the moment term, the control torque, and the other moment is the moment due to the weight. So there are just two moments acting on that bar. So the total moment becomes the sum of these two. And on the right hand side we have the mass moment of inertia times the angular acceleration. Okay, so in this case the equation for this system becomes this equation here. So if you look at this equation, this time we have a nonlinear function of theta, right? Due to this the trigonometric relation here, we have this sine theta term, and because of that, this is a nonlinear system, right? Because when you look at the equation, you have this sine theta, and as we know, sine is a nonlinear function. It is still a dynamic system because we have derivative terms in our equation. Okay, and if you look at, consider this as a system, the input, this time we can say that there are two inputs. One is the control torque. So this is something we can change. That's our control input. And the gravitational acceleration also has an effect on the output, right? But since we cannot control that, this is our disturbance input. So we represent G as a disturbance input to our system. And for the output, we can use the angular position or the angular speed, for example. These can be considered as possible outputs for this system. Okay? So we could have added additional elements to this system. For example, we could have added like a rotational spring here. So we can, so if we had a spring like that, then that would bring additional moment to this bar, right? So if this is theta, that would bring an additional moment, and it would be in the direction opposite to the mass, so that would bring an additional term like, ya böyle küçük küçük noktalar ki her tarafta çok sinir ediyor beni. So if we had this spring element, then that would be Tc plus m times g times L over 2 times sine theta minus some constant times k theta. Okay, so this was an easy example. Okay, now I think we can talk about the concept of degree of freedom. So this is a very important term, and we can easily define what degree of freedom is on these simple examples we just saw. Okay, so here's the definition of degree of freedom. It is number of independent displacements and rotations that specify completely displaced or deformed position or orientation of the body or system. So in other words, you have a system, okay, and you take a picture of that system, and to express the position and the orientation of the system, how many variables you need. So that becomes the degree of freedom. Okay? Okay, so I guess we can go back to these examples and we can talk on these examples. So in the first case, example, there was a mass, and this mass had freedom to move along this horizontal axis only, right? So this can go along, slide along that horizontal axis. So if I take, suppose the system in motion, and you just take a snapshot of the system in motion, and when you look at that snapshot, for this case, only one variable is sufficient to tell its position, and that would be the position of this mass along this axis, right? So if I look at the picture, and if I measure the position with respect to some fixed reference, so this y value, it is like half a meter, I don't know, 2 meters. So that number by itself is sufficient to completely describe that picture. So that means that system was a 1 degree of freedom system. Okay? Now let's come back to the pendulum example. This time, if you take a picture of this system, then this can only move along, rotate around this A point, right? And the angle it makes with some fixed reference is sufficient to express its, describe its position, right? So that makes it again a 1 degree of freedom system. Okay? So if we had two masses like this, so how many variables you need to represent the position or the orientation of the system? It's just true, right? If as long as they can only move along the horizontal axis. So you have two masses, and you need to knowing the position of these two masses is sufficient to express the complete picture. Okay, so let me go back to the pendulum example. So we said that this is a 1 degree of freedom system. It's only rotating around this axis. But if I add a second element to this pendulum, like the 2-bar pendulum, this time the degree of freedom is now 2. So again, this is a single axis joint. Similarly, you have the same joint here, so this can rotate freely around this point. So by using two coordinate axes, you can describe the position completely. So for example, you can choose one axis as this one here, so let this be your theta 1. Or theta 2 you can define in different ways, but for example, this can be how you define your second coordinate axis. So this is a second degree of freedom, and this system now has a total of 2 degrees of freedom. Okay? So if you take a spring mass damper or spring mass system like this, so if it's moving along this axis only, this is 1 degree of freedom, so this is your only degree of freedom. But you can also imagine, you can also have a pin joint here, and then have this entire system free to rotate around this point, A. So such a system will have 2 degrees of freedom, because you have one coordinate axis is required in this direction to represent that position, and then you need a second one to represent the position in this axis. So that means you have a 2 degree of freedom system. Mm-hmm. Doğru, onu konuşalım. Okay, so let's go back to this spring mass system. So when you constrain the motion to one axis only, think of it as a train, okay? So it can only move along some rail. So it can move only along that axis. So this is a 1 degree of freedom system. But if you consider that this can also move in the other direction, in the horizontal plane, so I don't know, let me call this, if this was your y-axis, and if there was freedom in the lateral direction as well, then this would be 2 degree of freedom system, because it can move along this axis and also it can go along this axis in the horizontal plane. So that's 2 degree of freedom, but still there's no vertical motion. So if you add the vertical freedom to that, so if you consider now the z-axis in addition to these two, so this time you have a mass, it can go in this direction, it can move in that direction, and also it has this freedom. Now this is you have a 3 degree of freedom system, but still notice that there is no rotation allowed here, right? So the mass is attached to this spring and it doesn't allow it to rotate. So this is a 3 degree of freedom system. But if you somehow have rotational freedoms, then each freedom will add to your degree of freedom. So that being said, the general motion in 3-dimensional space is 6th of. So that's, I guess, what you are referring to, right? So if you have consider any object, like consider a helicopter, for example. So a helicopter can move along all 3 axes, right? So it has 3 degrees of freedom, translational degrees of freedom. But then, in addition to that, it can rotate around all these 3 axes, right? So it has freedom to pitch and roll and yaw. So these add 3 more degrees of freedom. So the most general motion of a rigid body in three-dimensional space has 6 degrees of freedom. So if you consider my explanation before, so if you see a helicopter flying, you take a picture of that, and to represent the orientation and position of the helicopter, you need 6 variables. So you will need 3 of them to indicate its position, and then you will need 3 angles to represent its orientation with respect to the Earth. Okay? Do you have any questions? So this degree of freedom is also a very important concept, and so obviously systems with more degrees of freedom are difficult to study, because for each additional degree of freedom you need to write a different separate equation. So in these 2 examples we had just 1 degree of freedom, and it was sufficient for us to write that Newton's equation once. But if you have a second degree of freedom, then you need to write additional equations for additional degrees of freedom. And that's why we, instead of the entire motion, we most of the time consider simplified motions. For example, for studying aircraft, instead of this complete 6 degrees of freedom, in many cases we only consider longitudinal motion. The longitudinal motion is a restricted version of the 6 degree of freedom motion, right? In the longitudinal plane, you are not allowed to go in the lateral direction, so you lose 1 degree of freedom there, and you are not allowed to do the rolling and yawing rotations. So 2 additional degrees of freedom are removed. So in the longitudinal plane, you have just 3 degrees of freedom. Okay, so let me just look back here. Okay, so I think this is a nice example, so let me just quickly talk about this. So if you consider, instead of a rigid pendulum, a flexible pendulum, then you have a different situation. So if you have a flexible bar, then when you take a picture of that while moving, you can't just express the entire picture by using 1 rotation only, because depending on how it was moving, it will have a deformed shape, right? Since it is flexible. So when you look at the picture, it can have any of these possibilities, right? So the theta is just 1 angle, so you can define 1 theta here. But using that single number, you cannot give the complete shape here. And if you want to give the exact shape, you need to have infinitely many numbers, because you need to know the theta at every location of this bar. So since it is a flexible structure, there is a distributed parameter system. And again, to study the exact motion, you need to consider, so this is a system with infinite degrees of freedom. But what we can do is, we can approximate it with a lumped parameter model. So instead of the flexible bar, we can divide it into 2 parts, for example. And now we can consider these 2 are rigid bars. Okay, so this is rigid, and this is rigid. And when you, this time, you can describe the entire motion by 2 variables, and these 2 are these 2 coordinates, theta 1 and theta 2. Okay, so now you approximated the actual flexible bar with a bar that is composed of 2 rigid bars. But obviously this can only express this bending motion, which is, well, you haven't taken the vibrations course, so it doesn't make sense for me to talk about vibration modes. But this is in fact the first mode, so you can only see the first mode of the bar. So if you want to be more accurate, you can consider more elements, right? So if, for example, you can add a third element here by defining a third variable here. So this is a system with 3 degrees of freedom. So this is a step closer to the real system. So this time, in addition to this motion, so this flexibility, I should be draw them better. So this is how a flexible bar can be deformed in the first mode. You can also see things like this. So you can see the second mode. So you have this higher order shape. And as you add more elements to this system, every time you add an element, you make it closer to the real flexible system. And every time you add an element, your equations get more and more complex, right? So if you just have two elements, so for one rigid bar, you had one equation, right? So you had this equation only. The total moments are equal to inertia times theta double dot. If you have the second element, then you need to write a similar equation for that second. So every time you have a degree of freedom, you have an additional equation. Okay? So let me now go back, show you an additional example for a mechanical system. So this is an example I really like. So this is the car suspension problem. So let me just try to do it quickly. So we're considering a car like that, and we're just looking at this part, okay? So if you take a close-up view, what you have there is you have the wheel, and then between the frame of the car and the wheel, you have a spring damper system. So if you look at what's happening there, you will see a spring and a damper. So this is how a car suspension system looks like. And in reality, there's really a spring and a damper there. If you look at a car shock absorber, they look very much like this. So there's a damper in the middle. So there's a piston, which is this damper. And then there's a spring in addition to that. So it is really like, the situation is like that. So you have a mass. And there's a spring and a damper. And then there's this wheel. Okay, so here this mass, we'll call this MS. So this is the mass of the entire car divided by 4. Since there are 4 wheels, the total mass is divided into 4. So this is an approximation. And then there's this wheel. Okay, so if you want to model this, you have several options. For you can consider the wheel itself to be a rigid object, rigid mass. In that case, you can just continue with this model. But in fact, it's not really rigid, right? The tire is air filled, and it has certain flexibility. So if you want to add that effect into your model, here's how you do that. So you take this mass of the car, and then there's a spring and a damper, and then you consider another inertial element, and this is your wheel. So this is of the wheel, and then you add another set of spring and damper, and these are used to model these model the stiffness and damping of the tire. Okay, so let's say we want to model this car suspension problem. Okay, so we have two inertial elements. We have one mass here, which is the mass of the car, and then we have another element here, which models the wheel. Okay, and it is sufficient to consider only the vertical motion of these things, right? Which is obviously the significant motion here. So we will make the assumption that this mass, the car itself, can only move up and down in the vertical direction. So there's 1 degree of freedom for this mass, and then there's a separate mass which can move independently. Since there's a spring damper connection here, the wheel can move independently from the car itself. So this is in fact a 2 degree of freedom system. Okay, so so this is my first coordinate. Let me call this y. It's ys, I think. It's what I called it before. And then I need a second coordinate to represent the position of the wheel, and let this be yw. And remember, we should all be checking these positions with respect to some fixed reference. And what this is, this is the position of the road surface. Okay, so I'm going to give this another yr. So what this represents is the surface of the road. So if you are driving along a straight road, then yr is a constant number. But if there's, for example, a speed bump like this, then this speed bump will cause the wheel to go up, right? So if you are driving here while going over here, your wheel will be raised, and this yr represents the road. So this yr is the coordinate of the road surface. Okay, so to model this car suspension system, we have two masses. One represents the car body, and so to write the spring and damper forces, let me do what I did before. Let me make the assumption that ys is a positive number, and then it's moving in the positive direction, which means y start is also positive. In this case, since y is positive, this means that the spring here is extended, right? And under that condition, the shock absorber spring will be providing a force to bring it back. So this is going to be the force due to that spring. So let me define some parameters. This is a spring constant for the shock absorber, and for the wheel I have different parameters. So this force is going to be Ks times okay, so this is a tricky part. So the spring force depends on the how much the spring is deflected with respect to its neutral position, right? So I cannot express that by using ys alone, because it depends on the relative distance between the car and the wheel, right? So to be able to model that, I need to know the position of the wheel as well. So in addition to this, I need to make additional assumptions here. So let me say that ys is greater than yw, and that is greater than 0, and also ys dot is greater than yw dot, it is greater than 0. Now I can write the spring and damper forces. Okay, so here's the situation. In equilibrium, we have the following situation. So we have one mass here, another mass here for the wheel, and then these have a certain deflections. So what I'm saying is I'm writing the forces in an instant where these are true. So what does this tell us? The spring, the wheel has a position that is higher than the equilibrium position, right? So our reference is still the same. So yw is greater than 0. So what does that mean? Yw is raised a little bit. So the wheel is raised. And ys is also greater than 0, but also it is greater than yw. So that means the car itself is also elevated, but the amount it's elevated is higher than this difference here. So I'm taking this as the 0 position for yw. Okay, so the equilibrium positions are taken as 0. So yw positive and ys is also positive, but it's greater than yw. So that means this spring is extended. This spring is also extended, right? Okay, so now this is the picture for my assumptions. Okay, so this is the current situation. So in equilibrium we have this case, but now I'm writing the forces for this instance. So let me call that current instance. Okay, now let me write my forces. So let me bring these here. Okay, so this spring is extended. That means the spring force should be in the down direction. The magnitude should be equal to the spring constant Ks times the amount this has moved from the equilibrium position. In equilibrium, so we take the equilibrium this distance to be 0, but in the current situation we have Now the distance here is ys minus yw. Takip edebildiniz mi? Yani çok basit bir şey anlatıyorum aslında da biraz şey oldu. Olay karıştı sanki. We're keeping track of how the springs are in which direction they are applying forces. So in the relaxed or in equilibrium condition, we take the spring forces to be zero. And under this case where ys is extended and yw is also extended, by ys is extended even more due to this assumption. That means this spring has a wider deflection compared to the equilibrium position, and the difference is given by this difference, ys minus yw. Okay? And we can write the same thing for the dampers. For the dampers, we just replace the positions with the dot terms. Now we need to write the forces for the other mass, which is the mass that represents the wheel.
Burada dengeleyici kuvvet nerede olacak?
Dengeleyici kuvvet derken?
Yani şimdi aşağı yönde gösterdik onları. Ve M de aşağı yönde olacak. Bunu sıfır olması gerekiyor ya.
Çok güzel bir şey sordun. Öyle olması gerekmiyor. Ya ben şu anda hareket halinde yazıyorum denklemleri. Okay, so let me just repeat this in English. So I'm writing these forces for I took a snapshot, and it doesn't have to be an equilibrium position. Okay, so if you look at this, in fact, they are moving, right? So if you look at my assumptions here, they are in motion. So both of ys dot and yw dot are positive. That means they are in constant motion. So imagine like this, like the case. So you were driving and you hit a speed bump, and your car started jumping, and you just took a picture while it was moving up. Okay, so this is the situation for that. So the forces don't need to be in
equilibrium.
So obviously there should be the gravitational force here, which I didn't include. But that gravitational force is taken care of by the equilibrium deflections of the springs. So normally there's a weight, this has a weight, and this has a weight, and these weights cause the equilibrium deflections here. So if you consider this equilibrium, there's a spring force here, that this spring force balances the weight of this thing here, and the spring force here balances the weight of this entire structure. But I'm just, by taking these to be zero, I'm assuming the following. I'm saying that the equilibrium values are different than zero, but there's also the weight. And when you write the equations for the equilibrium, the weight terms are cancelled by the equilibrium values of these springs, and hence I can take the equilibrium values to be zero. If that makes any sense. Okay, so let's continue here. Now, for this, the car itself, there are only two forces. These are the forces due to spring and damper. Again, normally there should be the weight, but I'm just neglecting it for this example. And for the wheel, there are four forces. There are two forces due to these two elements, and then there are two more forces due to these elements here. This spring was extended, right? So this a spring in extension tries to pull it both ends back together. So it is pulling this mass downwards, but it pulls the lower mass upwards, right? So the spring force, the same force here, acts on the lower mass in the opposite direction. So this is similarly the same damper force appears here in the other direction. And then there are two additional forces. But since this spring is also in extension, it will apply a force trying to come back to its equilibrium position, which means it will try to pull the mass downwards. And now this deflection is going to be YW minus YR, right? So I forgot to show that here, but normally so this should be wheel, right? Not S. So anyway, our time is over, so let me stop here and I will continue with this car suspension example tomorrow.